Uh, Raut sir, shall we start?
Yes, sir.
Okay. Am I audible?
Yes, sir, you are audible.
Okay, thank you. Uh, Good evening, all. I welcome all the participants for day two sessions. The first session for day two. Today, we have with us Mr. As a speaker, we have with us Mr. Dr. Laukik Raut, sir. Uh, Let me take a privilege to introduce Dr. Laukik Raut. Currently, he is assistant professor at a GH Rasuni College of Engineering, Nagpur. Dr. Raut has a 2 years of industry experience as a production engineer and in manufacturing utility. He completed his Doctor of Philosophy at VNIT Nagpur. Uh, he has three patents to his name. He had received more than 1 crore of grant for the various projects. He has guided more than 33 projects as a for MTech students and BTech students. Dr. Laukik Raut has a very good citation in terms of his publication, and two of his paper has more than 700 citation in a less than a 2 years of period. So we can uh, we can understand how on his work during the PhD work is very important based on the citation. He has attended and published papers in more than 16 international and 19 national conferences. One book chapter he has also published. He has three copyrights to his name. He has attended more than 10 STP and FDP, and equally he has organized the same STP on various topics related to material, CAD/CAM, additive manufacturing. He was awarded with a special prize at the hands of Dr. Nitin Raut, Cabinet Minister of Government Maharashtra of then, for guiding the project titled Design and Fabrication of Agriculture Seeder Weaver Machine. Uh, he is continuously working as a reviewer for the various reputed journals. Uh, uh, Also, he usually conducts workshop and trainings on additive manufacturing, CAD/CAM for the faculty and industry person as well. So I welcome Dr. Raut sir for this 6 days online faculty development program on the advanced materials, 21st century materials, advancement in science and technology. So I think without wasting a time, I'll hand over to you and I request you, will you please start the session.
Thank you, sir. Thank you so much. So, first of all, I will share my screen.
Okay, let me stop my, okay. Sir, you can now share your screen.
Okay. Okay. So, is my screen visible?
Yes, it is visible. So do it in a slide mode.
Yes, sir. Yes, sir. I'm doing. Okay. So, first of all, thank you so much. And thank you so much for inviting me here as a resource person in this ATAL FDP on 21st century material, advancement in material science and technology. Thank you so much to Cummins College of Engineering for UMATS, and special thanks to my best friend, Professor Prasanna Mahankar. So today I will be talking on manufacturing of functionally graded material, that is FGM, by wire arc additive manufacturing. So this was my PhD topic, and here I am explaining my PhD work through this presentation. So if we need a material properties in such a way that one side one side it has one kind of property and on other side it has different kind of property. So with a single material it is not possible. Suppose we have some material, suppose we have some material and we want properties like, sorry, suppose we want high hardness, on this side and high toughness on another side. So this is not possible with a single material. And hence we have to develop different kind of material, and that material can be known as functionally graded material, which will offer two type of property. So on one side we will have high hardness, and on another side we will have high toughness. So we have to develop a new method for developing this material, and that material is known as functionally graded material. So suppose this can be understand with another example. Suppose we have a material like this, okay, and suppose we are adding different layers over this material, okay, and suppose the base layer has the hardness say 200 HV. Suppose here the hardness is 200 HV. It is very difficult to write with this pencil, and I'm not habitual with this. So please try to understand. So suppose we are varying the hardness with a different layer. So a single material will give you different hardness as with a different layers. So this is possible with functional graded material. So we can gradually change the properties of the material with the help of FGM. One more example I would like to give. So first of all, I will clear the concept of FGM, and then we will proceed. So suppose we have a material, okay, and it is tough in nature. So this material is tough in nature, okay. And now suppose we are reinforcing the ceramic particle inside it. So suppose we are reinforcing the ceramic particle here. And now again, while reinforcing the ceramic particle, again we are changing its concentration. So we are here you can see we are reducing its concentration. So here what will happen if we go from bottom to top, its toughness will be decreased. Here you will be getting higher toughness. Whereas if we move from top to bottom, its hardness will decrease. Here there will be highest hardness. On upper side there will be highest hardness, and if we go from top to bottom, the hardness will decrease. So the same material, we can include two different properties, and that too, that is gradually either increasing or decreasing when we are moving from top to bottom. And this can be achieved with the help of functional graded material. So I think the functional graded material is cleared here. So now we will move further. So, so these are the contents of my presentation. So the introduction. So functionally graded material are the composite material which are designed to present a particular spatial variation of their properties. So as we are moving from top to bottom or from bottom to top, the properties are gradually changing. This is usually achieved by forming a compound of two components whose volume fraction is changed across the certain direction. So along one direction, the properties are changing. So these are the different applications of functionally graded material. That is, it can be used in nuclear reactors, space application, medical applications, communication, energy, and some other applications like building material, window glass, wood goods. So these are the applications of FGM. Now, why these FGMs are required? So if you consider an example of gear, so the body of gear must be tough, whereas its surface must be hard and wear resistant, right? Because the gear, it is working in certain environment that it should be very tough. It should absorb the forces. So it should be tough at the center, whereas its surface must be hard and wear resistance as it is in continuous contact. Then you can take an example of knife. So a knife needs only to be hard at its cutting edge. Elsewhere, the material must be strong and tough. So here also at the surface, we want that material should be strong and tough, whereas it should be sorry, at the center, the knife should be strong and tough, whereas at the surface it should be hard, so as to cut the other material. So what is the benefit? The stress concentration is reduced because we are if the transition from one material to another is gradual, because we are gradually increasing or reducing the concentration. So stress concentration is very less. Now there are various processing techniques with which we can manufacture the FGM. like vapor deposition technique, plasma spraying, ion beam assisted deposition, then powder metallurgy, centrifugal method, and additive manufacturing. In my research work, I have used additive manufacturing, that too wire arc additive manufacturing, for manufacturing the functionally graded material. Here you can understand one of the method of manufacturing the FGM. So here they have used die and the punch. So here they have taken two different material A and D, and they are varying their concentration. So at the lower level, you can see 100 gram of material A, upper level 70 gram of material A, 30 gram of material B. Likewise, at the top layer, there is 100 gram of material B. So then it is manufactured with the help of this die and bunch assembly. And here you are getting the FGM structure. Now in each layer, you will be getting different properties. So this is not possible with the conventional material, and this can be achieved with the help of FGM. Then, as I have already discussed, I have manufactured the functionally graded material with the help of additive manufacturing. So this is the classification of additive manufacturing. So it is broadly classified into four categories, that is binder jetting, powder bed fusion, sheet lamination, directed energy deposition. Now this directed energy deposition, that is further classified into three categories, and I have used this technique, that is wire arc additive manufacturing. So now we will understand what is wire arc additive manufacturing. So with this diagram, you can understand the wire arc additive manufacturing. So in this process, we can use existing welding techniques like MIG, that is metal inert gas, or TIG, that is tungsten inert gas, or plasma arc welding. So here we can use an existing welding technique. So as you know, the arc is generated in between electrode and the substrate, and that arc is utilized to melt the material. Now, basically, the welding method is a joining method where we join the two different material with the help of welding. But here we are using welding method for depositing the material, because now the arc is generated and we are supplying the electrode or feeder wire. So that feeder wire can be deposited layer by layer. So here you can see this is a TIG method, that is tungsten inert gas, GTAW method. So here you can see the arc is generated, and here we are using the filler material. The electrode is of tungsten, and that filler is deposited layer by layer. So here we are using welding method to deposit the material. So welding method we are using as an additive manufacturing method. That is why this method is known as wire arc additive manufacturing. That means the electrode is in the form of wire. Here you can see the filler metal, that is in the form of wire. The arc is generated. So the source is electric arc, and that electric arc is utilized to melt the material. Hence, the method is wire arc additive manufacturing. I hope this method is clear to you. Then, so in additive manufacturing, all of you must be aware about it. So basically, we develop the CAD model. That CAD model, uh, then we convert that file into STL format, and it is then transferred to 3D printer. And then that 3D printer deposit the material layer by layer. Here you can see. So this is the additive manufacturing technique. Now, what I am discussing, that is wire arc additive manufacturing, where we are using existing welding method. So in previous diagram, I have discussed GTAW method, and here I'm using GMAW torch, where the electrode is in the form of wire. So the arc is ignited in between that electrode and the substrate, and that electrode will be deposited layer by layer. So this method is known as wire arc additive manufacturing. So why we use this wire arc additive manufacturing? The main reason is highest deposition rate. So there are certain other additive manufacturing technique like laser-based methods, but there the material deposition rate is 2 to 10 gram per minute. Whereas in wire arc additive manufacturing, the material deposition rate is around 50 to 130 gram per minute. So this is the biggest advantage. So when you compare with the other additive manufacturing process, its rate of deposition is quite high. Then the warm is less costly, as we are using existing welding techniques. So GTAW, GMAW, these methods are very economical. These machines are very economical, and we are using those machines to deposit the material. So VAM is less costly as compared to laser-based 3D printers. Then the material handling efficiency that reaches to 100%. So here the material is in the form of wire, and entire wire can be melted and deposited over the material. So material wastage is around means very less. We can say 0% in this method. Whereas if we use laser as a source, and if the material is in the powder form, in that case there is a material wastage. So here the material handling efficiency is 100% in case of wire arc additive manufacture. Now, now I will tell you what exactly the process, what we do in wire arc additive manufacturing. So we are using wire as a feedstock, that is raw material, and then electric arc is generated. So electric arc as a heat source to melt the material, and then we are depositing the material layer by layer. Now, how the motion is provided. So either we can use the robot for depositing the material, or we can convert our existing CNC machine, like vertical CNC machine, for depositing the material, because there also you are getting motion in three different direction, X, Y, Z. So you can, for research purpose, you can modify your existing CNC machine for depositing the material. And if you have robotic system in your institute, in that case, you can use that system for depositing the material. So this is the setup for the wire arc additive manufacturing technique. So here you can see this is a 6-axis robot, and that is attached to the welding source. This is the wire feeder. This process is known as GMAW process. So the wire will be in the form of the electrode is in the form of wire, and it is then supplied to this torch. The torch is attached to the end effector of this robot. Now this torch will deposit the material layer by layer. So here you can see this is the additively manufactured structure with the help of this setup. Now again you can modify the existing setup. So here you can see the vertical milling machine. Now they have converted this vertical milling machine into the wire arc additive manufacturing setup. So because with the help of VMC you can get the motion along x-axis. So you can move this table along x-axis, along y-axis, and you can move the spindle along z-axis. So simply you have to replace that spindle, and to that end you have to attach the welding torch. Now the arc will be ignited in between your substrate and the welding torch, and then you have to move this table along x direction. After depositing the first layer, again you will lower down the table along y direction. Then again the arc is ignited. Then you can deposit the second layer. So likewise, you can deposit multiple layers, because this spindle will give you the motion along z-axis, whereas this table will give the motion along x-axis. So with the help of this, you can deposit a wall-like structure, or you can deposit a block. There are limitation of this setup, because you cannot deposit a complex geometry with this setup, because you are getting motion along XYZ axis, only 3 degrees of freedom are there. Whereas with this setup, you are getting 6 degrees of freedom. So it is possible to deposit a complex geometries with the help of this setup. So that is the benefit of robotic system. But if you don't have a robotic system in your institute, in that case, you can modify the VMC machine that is available in the workshop, and you can deposit, or you can carry out your research work. So the process parameter, so here wire feed speed, that is one of the process parameter. So wire feed speed, that is rate at which the wire is feed through the torch. Then travel speed, that means speed with which we are depositing the material. So speed with which we are moving the torch, that is travel speed. Then the current and voltage. So these are the independent parameter that can be set for your research work. Now, we can use three types of energy source in wire arc additive manufacturing. That is gas metal arc welding, that is GMAW, then gas tungsten arc welding, GTAW based, or plasma arc welding. So in most of the college, you can find this GMAW machine and the vertical milling machine. So you can attach your GMAW setup to uh, that vertical milling machine, and you can carry out your research work. So here we can understand. Here we can see the GMAW process. So the electrode is in the form of wire, and the arc is generated in between arc and the substrate, and hence the material is deposited. This material you can deposit layer by layer. So we are using existing welding technique, not for the joining, but for the deposition. So this is commonly used method. Uh, the wire, the electrode is in the form of wire. Here the deposition rate is around 3 to 4 kg per hour. This is the beauty of this method. We can deposit around 4 kg of material in 1 hour. Whereas with traditional 3D printers, it is the rate of deposition is very less. Today only I have deposited one part whose dimension is I think 20 centimeter length, breadth, and height. And we need around 5 hours are required to deposit with the help of our 3D printers. So, but here the rate of deposition is 4 kg per hour, so we can deposit very large component. Some drawbacks are there like poor arc stability because here we are consuming the electrode. Spatters you can observe. It is suitable for aluminum and steel, and it is not suitable for titanium. Then the second method, that is GTAW. So the electrode is in the form of we are using here tungsten electrode. So additionally, you have to use a filler rod because this is non-consumable in nature. So we have to use here filler rod. So this is a GTAW process. So non-consumable electrode is used. So here we have to use separate wire feeder. Then the rate of deposition. So its rate of deposition is less as compared to GMAW. Here the rate of deposition is 1 to 2 kg per hour. Then it is difficult to automate this process because here we have to automate the movement of torch as well as filler rod. Whereas in GMAW process, we have to automate the movement of this wire, this electrode only. Whereas in GTAW, we have to automate the movement of these two different elements. So it is very difficult to automate this setup. So complicated robot programming is there, but this is suitable for titanium. Then this is plasma arc base. Again, the same method. So here we are using the electrode, uh, the tungsten electrode. So it is non-consumable in nature. And separate wire feeder we have used, separate filler wire we have to use in this process. Here the rate of deposition that is more as compared to GTAW, that is 2 to 4 kg per hour. So again, the drawback is wire and torch rotations are needed. So two elements we have to automate. Different metals we can deposit with this method, that is titanium alloy, aluminum alloy, steel, nickel-based superalloys, magnesium alloy, and even we can deposit two different materials like steel and nickel alloy. So bimetallic combinations are also possible with the help of wire arc additive manufacturing. The defects, so defects are common. The defects which we observed in welding, same defects we can observe in this method. That is deformation of the component. Residual stresses are also there because each layer is deposited, then it is allowed to cool, then we depositing the next layer. So there is a complex thermal history. Each layer is subjected to different temperature. So that is why there are residual stresses. Porosity, sometimes you may observe crack, delamination, oxidation, low surface finish. So these are some of the defects in this method. But as far as surface finish is concerned, we can remove the upper layer so as to get a good surface finish. These are some of the applications of wire arc additive manufacturing. So here you can see this is the shell of a projectile. Its height is around 2 feet, that is deposited with the help of this wire arc additive manufacturing. Even such complex jobs, they can be deposited with the help of worm. Then this is very long component. This is the boom of, here you can see the boom of JCB. So this complete boom is deposited with the help of wire arc additive manufacturing. This is not possible with other additive manufacturing technique because there are size limitation. We have to purchase, and the metal 3D printers, they are very costly. So it is very difficult to deposit a component like this with other additive manufacturing. But with WAM, it is very easy. because we need a robotic setup, and with that robotic setup we can deposit a component like this. Even the scientists or the authors have deposited a large component like this with this method. So these are the applications. Now this is the comparison GTAW, GMAW, and plasma arc BESS. So we have already discussed the deposition rate. In my research work, I have used cold metal transfer welding technique. So this is an advanced welding method. This is an advanced method to the GMAW, because the drawback of GMAW process is poor arc stability and spatters, and that those drawback, and even there is high heat generation inside the deposited component. And in cold metal transfer welding, the the heat that is get accumulated, that is very less. So I have used cold metal transfer welding to deposit the components. Now this is cold metal transfer welding process. So this is the variant of GMAW process, the advanced variant of GMAW process. So again, the electrode is in the form of wire, and this process is designed to reduce the heat input, because the major drawback of GMAW process is heat input is very large, and that is why there is deformation. So here the heat input is very less and minimum distortion is there. It is developed by Fronius. So here you can see the CMT working. And then these are the papers which I have gone through. So I have categorized those papers based on their objectives, process, the material the people have deposited, positioning system, specification of the component, and their measure findings. So I will not discuss it thoroughly. So these were the literature gaps, those that were identified that time. So most of the researchers have used laser as a source, but we are using here as a welding technique. Then GTAW, GMAW, most of the researchers have used these methods. But in my research work, I have used an advanced method, that is CMT. Then I have deposited two different material. What I have observed that the people are depositing only single material, but I have deposited two different material, that is austenitic stainless steel and low carbon steel. Then I have studied its corrosion behavior. So these are the objectives, that to manufacture a bimetallic structure, then to study its microstructural feature and mechanical characteristics, then to study the corrosion behavior of that bimetallic component. After that, to develop the mathematical model to find out the optimum process parameters. Uh, the independent parameters were torque speed, voltage, wire feed speed, and the response like bead width, bead height, and its micro hardness. Then I have used machine learning techniques to establish the relationship between the input parameter and output parameter. So I have used an advanced algorithm, that is XGBoost algorithm, to establish the relationship between dependent and independent parameter. This is the methodology. I will not go in detail. So now, now these are the two materials I have deposited. This is the nominal composition of austenitic stainless steel. The grade is ER316 LSI. Here you can see the composition. The second material, that is low carbon steel. This is the composition. And these two material are deposited over the substrate. The substrate is of mild steel. So I have ordered the material from Ador Welding Limited. The diameter of both filler wire was 1.2 mm. For deposition, I have used CMT welding machine. It was developed, it was a product of Fronius. The model number is TPS 400i. So first of all, I have to select the process parameter, because through literature review, it was very difficult to get the exact process parameter. Now what I have decided, that I will deposit a wall with width 6 mm. So for deciding the process parameter, then I have deposited multiple beads over the plate, and then I have taken a cut section of it, and then I have observed its width and height in SEM machine. So with this process parameter, uh, I got the length of the bead as 6 mm and height 2.5 mm. So these are the process parameters. And for getting those process parameter, I have to deposit multiple beads. I have to perform number of experiments for getting the width as 6 mm. So these are the process parameters. So both the materials I have deposited with CMT machine. This is the current for low carbon steel. This is for austenitic stainless steel. This is the voltage. This is the torque speed in mm per minute. This is wire feed speed in meter per minute. These are the shielding gases which I have used. The shielding gas flow rate was 15 liter per minute. Then I have maintained the interpass temperature as 200 degrees Celsius. Now, what is interpass temperature? So uh, suppose we have deposited the first layer. So it is at certain temperature. So I wait so that the temperature come to 200 degrees Celsius, and then I have deposited the next layer. Again, I wait for some time so that the temperature reaches to 200 degrees Celsius. After that, I have deposited the third layer. That means I have maintained a constant interpass temperature so as to get uniform properties across the deposition. Then this is the polarity, that is direct current electrode positive for both deposition. This is the setup available at VNIT. So we have a Phoneus machine. We don't have robo in the Department of Mechanical Engineering that is attached to CMT. We have a robo, but that the power source was GMAW. But here I want to use CMT, and for that CMT, the robot was not attached. So that is why we have developed our in-house setup for the deposition of material. So this is the lab jack, and we have attached that setup to that lab jack, and we have deposited various layers with the help of this setup. So this is the deposition. So one wall I have deposited. Here you can see the layered structure. So the lower part is made up of low carbon steel. Upper is of austenitic stainless steel. This is the length, 150 mm, sorry, 150 mm is height and 160 mm is length of that wall. So what I observed, the wall surface is layered structure. Here you can see the different layer. It is free from the defects such as crack, porosity that was not observed. So it reveals a sound deposition. So total 55 layers I have deposited. The average layer thickness was 2.7 mm. Low carbon steel, this portion. So total 30 layers are deposited. For austenitic stainless steel, 25 layers are deposited. This is the dimension. Then it is removed, the substrate is removed from this wall, and then milling is done. Again, this is the schematic where you can see I have taken various samples from this wall. So these are the tensile samples. So two samples I have taken from austenitic stainless steel, two samples from low carbon steel, and these are the interfaced. Okay, and these are the samples for the optical study, SEM study, EBSD, then EDS for corrosion study. Uh, these samples were taken out from the wall. So the sample for metallurgical study size is 1 centimeter by 1 centimeter, and for tensile sample, ASTM E8 standard was followed. After that, the grinding is done. After grinding, polishing is done. So different papers I have used like from 400 to 2500 grit number, and then the cloth polishing is done. After that, the etching is done. So ASS is done. I have used electrochemical etching. In oxalic acid, I have done the etching. And for LCS sample, nitrile is used. Then for corrosion study, I have performed DLEPR and PDP test for to study the corrosion behavior of the deposition. Now here you can see the microstructure of the upper part. So this is the upper part, that is austenitic stainless steel. Then I have taken three different samples from three different locations, the upper, middle, and the bottom. So this is the optical micrograph of upper part. So here you can see randomly oriented grains. So as no new layer is deposited over this, so heat is rapidly convected away. So hence we were getting here randomly oriented grains. This is the microstructure for the middle part. So here you can see the dendrites of austenite. These are the dendrites, means the matrix is austenite, and here the vermis, the vermi-like structure in black color. These are the ferrites. So the microstructure consists of dendrites of gamma austenite and delta ferrite. Here you can see the columnar growth along the deposition direction. So with this microstructure, we can understand how the growth, how the grain growth takes place. Now here you can see this is the previously deposited layer. Now new layer is deposited. So while depositing the new layer, the part of previously deposited layer, it is again remelted. So here you can see the partial melting and clear distinction of two different layers. Now, for knowing the mode of solidification, because we have to finalize the phases. So with this only we cannot finalize or we cannot say that this is the exact phase. So for that mode of solidification that we have to understand. So this is the chemical composition. From this chemical composition, I have calculated chromium equivalent, nickel equivalent. So chromium equivalent, that is 23.73. Nickel equivalent is 14.28. Then I have calculated its ratio. The ratio is 1.66. If this ratio is more than 1.5, then it represents ferritic austenitic mode of solidification. So here I have observed Fa mode of solidification. So initially the material is in liquid stage. After that, you can see here liquid plus delta. That means delta ferrite starts formation. After that, liquid, delta ferrite, and then gamma austenite. So here you can see liquid, delta ferrite, and gamma austenite. When the nickel, chromium nickel equivalent ratio is more than 1.5. So liquid, after that delta plus liquid, then gamma plus delta plus liquid, and at the last you will be getting austenitic phase. So this is the mode of solidification. Then I have performed EDS analysis of ASS sample again to confirm the phases. So I have taken the EDS at two different location 1, location 2, and this is the chemical composition at location 1 and location 2. So at location 2, you can observe that the chromium is of 22.47 wet percent, whereas at location 1 it is 12.39. Likewise, nickel is here the nickel is maximum, here the nickel is minimum. So at location 2, chromium is maximum, that is it is ferritic stabilizer. So we can say that this is a ferrite, whereas this is austenite. So during the transformation of delta ferrite to austenite, the transformation of vermicular delta ferrite having chromium 22.47 to austenite does not take place, because here I am getting duplex microstructure, ferrite plus austenite. So this ferrite is not completely converted into the austenite. So this is retained ferrite. So again, it is confirmed with EDS study as well. Uh, then, uh, then I want to determine how much delta ferrite is present in that sample, because that delta ferrite again determines the property of that material. So again, we have a chromium equivalent and nickel equivalent. So intersection of that will, from this we can understand that the delta ferrite is in the range of 5% to 10% volume percentage. So here this is the intersection. So we can say that the delta ferrite is from 5% to 10%. So this can be predicted with the help of Schaeffler diagram. Again, I have used ferritoscope to know the amount of delta ferrite, as this is the theoretical method. So we have an equipment that is ferritoscope. With this we can uh, know the amount of ferrite. So I have taken the reading at three different locations: bottom, top, and middle. And these are the ferrite numbers. At the bottom, 6.6. At middle, it is 5.04. And at the top, it is 3.16. So again, this is the ferrite number is less than 10. And from this, we can say that from 5 to 10% volume percentage delta ferrite is available in that deposition. This is the XRD analysis of the deposition. From this, again, we can confirm that these are the phases, that is gamma austenite and delta ferrite. So this is the X-ray diffraction pattern for the ASS. And from this pattern, we can conclude that there are two different phases, gamma austenite and delta ferrite. Again, I have performed EBSD analysis over the deposition to know the crystallographic texture. What is the texture of the deposition? So this is the output of EBSD analysis. This is known as inverse pole figure, and this is the pole figures. So here you can see these are the grains, and they are oriented along one direction only. that is along the building direction. Okay, so here you can see that we can conclude that the preferred grain growth orientation is 0, 0, 1. They are oriented only in one direction. So this is highly textured material, and the texture is along deposition direction. Here also from this pole figure, so 0, 0, 1 maximum is 23.881. From this also we can conclude that the texture is along 0, 0, 1. Okay, so the orientation is along 0, 0, 1. So this is highly textured material. Again, I have performed the microstructural analysis for LCS part. So these are the microstructure of interface. So here you can see the clear distinction. This is LCS part, this is ASS part. And in LCS part, I have observed, in LCS part, I have observed the phases, that is acicular ferrite, polygonal ferrite, and the perlite. So these phases I have observed in LCS part. Again, I have performed the X-ray diffraction of LCS and the major phase, that is alpha ferrite. This is the EBSD analysis of LCS part. Here you can see the weak texture, whereas in this part they are oriented along one direction only. Here you cannot see any orientation. Okay, so weak texture I have observed in ABSD analysis for LCS part, and the phases were ferrite and cementite. Now I have performed the microstructural analysis of interface. So here you can see the optical micrograph of interface. This is SEM micrograph. This is EBSD analysis, and from this we can conclude the various phases present uh, in the interface. Then again, I have measured the ferrite along the interface. So this is for ASS part. So here you can see the ferrite number is very less to 10, and these are the ferrite number for LCS part. So the LCS has ferrite number in the range 115 to 130 because the major phase is ferrite, whereas for ASS the major phase is austenite. That is why less FN number. And there is sharp discontinuity. This is the interface. So when we move from LCS to ASS, there is a sharp decline in the ferrite number. Now this is EBSD analysis. So various elements here you can see this is the elemental map: chromium, manganese, molybdenum, silicon, nickel. So this is your LCS part, this is ASS part. So chromium is present in ASS part. So this is the elemental mapping, and I have taken the elemental mapping at the interface as well. So in the interface, you can observe chromium 5.52% and nickel 3.26%. So significant amount of chromium is observed at the interface. So that amount of chromium is get diffused in at the interface because of concentration gradient and temperature gradient. That also we can conclude from here. Then, as I have already told you, I have taken various samples. Here you can see the tensile samples from LCS part, ASS part, and from two materials. So then we have performed the tensile testing over that part, and these are the results for ASS part, for LCS part, and for bimetallic part. So the conclusion from this table are presented in conclusion set. Okay, so then I have plotted its stress-strain relationship of LCS, ASS, and bimetallic part. So here you can see that the stainless steel part having high toughness. This is for LCS part, and this is for bimetal. So the bimetal sample fractured on LCS side only. So whatever samples, two samples I have taken, and all both both samples were failed in LCS part. No sample failed at the interface. So there is strong bonding in between LCS and ASS. And then I have checked the micro hardness along the interface. So this is for LCS part, this is for ASS part. So the overall average micro hardness for LCS was 176. For ASS part, it is 168, and this is the micro hardness at the interface. So here you can see the maximum hardness. So the possible reason is the diffusion of chromium from ASS part to LCS part. because of temperature gradient or concentration gradient. Then I have performed the spectrography. So this is the SEM micrograph of fractured surface. So here you can see this is for LCS part. So I have observed dimple and voids, and this indicate a ductile fracture. This is the micrograph of fractured surface of ASS. Again, here also I have observed the dimples. So this also uh, we can say that there is a ductile fracture, and this is for the interface part. So all the samples they were filled in the LCS part. So again here also you can observe dimple and white. So we can say that the bimetallic part was also there was a ductile fracture in bimetallic part. Then I have performed the corrosion study of ASS part. So as you know that the intergranular corrosion that occurs in a stainless steel having carbon percentage higher than 0.02%. And in my case, the carbon percentage was 0.03%. So that will be vulnerable to intergranular corrosion. And when it is exposed to a temperature of 500 to 800 degrees Celsius. So both these two conditions were there. So that means there will be a intergranular corrosion. So in order to study that intergranular corrosion, I have performed DLEPR test over the over the sample of ASS. I have taken the solution H2SO4, 0.5 molar of H2SO4 and potassium thiocyanate 0.01, 0.01 molar. We have performed the DLEPR of that sample, and this is the SEM micrograph after DLEPR. So here you can see the microstructure is changed. So this is the chrome depleted region. That means the chromium is depleted from here and it is settled at the grain boundary and it is combined with the carbon. So there is a formation of chromium carbide at the grain boundary. And this is responsible for the intergranular corrosion. So the intergranular corrosion phenomena was observed in the deposition of ASS part, and that is confirmed with the help of DLEPR study. So I have performed the EDS analysis of this at two different locations. This is location number one, that is chrome depleted region, and this is second location. So here you can see at location 2, this is for chromium carbide. So highest chromium is observed. Whereas in chrome depleted region, there was less chromium. So the chrome is depleted from the region near to the boundary to the boundary. So these are the results of DLEPR. So mostly we observe degree of sensitization. So I have observed the sensitization. So three different samples were taken, bottom, middle, and top, and this is the DOS value. So the thermal conductivity of the deposited material, that is ASS and LCS, these are the thermal conductivity. And as I have deposited ASS over LCS, okay, that means the heat is rapidly conducted to the LCS because of its high thermal conductivity. And that is why I have observed low degree of sensitization at the bottom part. At the top part also, DOS is less as compared to middle because heat is rapidly convected. Whereas the middle portion, there was highest degree of sensitization because the temperature is highest in the middle portion. So that can be one of the reasons. Then I have performed PDP test, that is potentiodynamic polarization, to study the pitting corrosion. So there are different types of corrosion, that is intergranular corrosion, pitting corrosion. So to study the pitting corrosion, I have performed PDP test over ASS part, and this is the pit morphology. So after carrying out PDP test, I have observed the pitting in the deposited sample. So these are the pits. So the passive region, pit. Okay. So pitting hole of 180.9 micron is observed, and the cluster of pits are also observed in the deposited sample. Then this is the corrosion rate for ASS in miles per year. So both the phenomena is observed in the ASS part, that is intergranular corrosion and the pitting corrosion. After that, again I have performed the PDP of LCS part. We cannot perform DLEPR of LCS part because chromium is not there in low carbon steel. So we have to check its potentiodynamic polarization. So I have performed this, and here you can see the corrosion rate. So this is the corrosion rate for low carbon steel, and this is the corrosion rate for austenitic stainless steel. So in ASS, the corrosion rate is very less as compared to LCS part because of the presence of chromium. So that was the first objective of my study. The second objective was the optimization of process parameter, because we have to optimize the process parameters like voltage, current, wire feed speed, torque speed. So for that, I have used the technique that is ANOVA, analysis of variance. So this setup we have at VNIT, and GMAW torch is attached to it. So here I have taken the material that is ER70S6 low carbon steel. Substrate was MS plate. Then I have used Taguchi L18 full factorial method for the experimentation, because we want to reduce the number of experiments. The independent parameter was voltage, wire feed speed, and torque speed, whereas the response variable are bead width, bead height, and micro hardness. Uh, this is the deposition setup. So we have ABB Robo at VNIT, and the MIG welding machine is attached to it. So this is the nominal composition of low carbon steel, and this is the matrix with here you can see the different levels: level 1, level 2, level 3 for voltage, wire feed speed, and torque speed. These are my dependent parameter, that is bead width, bead height, and the micro hardness. So these are the independent parameter, and these are the dependent parameter. Now I have deposited 18 different beads over the plates. Here you can see 18 different beds. So these are the 18 different beads. So this is the complete matrix. So 18 different experiments. The This is the combination of independent parameter, that is voltage, wire feed speed, torque speed, and these are the dependent parameter: bead width, bead height, micro hardness. This is the SEM micrograph. These are the SEM micrograph of 18 different deposited beads. So I have performed ANOVA analysis over three different parameters, three different responses, that is bead width, bead height, and micro hardness. So this is response 1, bead width. So this is the ANOVA table for bead width. So the model was significant as the value is less than 0.0001. Uh, Here you can see the R square value, adequate precision, that is again more than 4. This is the equation for bead width. So from this, we can say that the voltage has positive effect on the bead width. Torque speed has negative effect. Here you can see torque speed has negative effect, whereas wire feed speed has positive effect. Then I have studied the combined effect of voltage and wire feed speed over the bead width by keeping torque speed constant. So here you can see, as we increase the voltage, the width increases because more amount of material is deposited. Again, as we increase the wire feed speed, again the bead width is increases. Then this is a combined effect of voltage and torque speed. Earlier it was wire speed. So as we increase the torque speed, the bead width will decrease. So there is inverse relationship and direct relationship in between voltage and bead width. Okay, so here you can see this is predicted versus actual graph. All the points, they are very close to the predicted one. Sorry, all the predicted point, they are very close to the actual one. Then this is ANOVA analysis for bead height. Earlier it was for bead width. This is for bead height. Again, the model was significant. R square value is 0.89. Quite good. This is the equation. And here the voltage has negative effect over the bead height. Voltage has negative effect. Here you can see. Wire feed speed has positive effect. Torque speed has negative effect. Then again, I have plotted it, the combined effect. So here you can see voltage has negative effect. So as we increase the voltage, it will flatter down. It will flatter the weld bit. So the width is increases, whereas height decreases. Okay. So here you can see, this is the graph in between predicted and actual. All the points are very close. Then the third response, that is bead micro hardness. So for bead micro hardness, this is the ANOVA table. Here you can see the p-value that is less than 0.001. So again, this model is also significant. R square value is 0.93. This is the equation. Here for bead micro hardness, voltage has negative effect. Torque speed, that is also negative effect. And wire feed speed has a, sorry, wire feed speed has negative effect. Torque speed has positive effect. Then I have plotted the combined effect of voltage and wire feed speed. Okay. So as we increase the voltage, the micro hardness decreases. So an increase in voltage leads to increase in heat input. So as we increase the voltage, heat input increases, which in turn causes decrease in the rate of cooling, resulting in decrease in micro hardness. Okay. So as we increase the voltage, heat input decreases, and that is why rate of cooling that is decreases. And as the rate of cooling decreases, there is decrease in the micro hardness. Then wire feed speed. So as we increase the wire feed speed, more wire is available for the deposition. So as the more wire is available, again the heat input is increases. So as the heat input increases, again there is decrease in the micro hardness that you can observe from here. So this conclusion can be drawn. Then this is combined effect for voltage and torque speed by keeping wire feed speed constant. So as the torque speed decreases, now we are decreasing the torque speed. That means again we are increasing the heat input, and that will decreases the rate of cooling, and that will decreases the micro hardness. This is the graph in between predicted and actual, and these points are also close to the actual one. Now, now here you can see the difference between experimental value and predicted value. So these are the 18 different experiments. These are the three different independent parameter, that is voltage, wire feed speed, and torque speed. Now this is experimental width. Okay, means the width of the bead, uh, the experimental values after deposition, whatever value I got, and these are the predicted values through mathematical modeling, and this is the percentage error. So here you can see the percentage error, and that is less than 5%. Then for uh, then for height, this is this is experimental and predicted. So this is experimental height, this is predicted height, and this is the percentage error. Again, it is less than 5%. So we have 95% accuracy. And this is for micro hardness, experimental, predicted, and this is the percent error. So these are the experimental versus predicted values, and they are very close to each other. This is for bead width, this is for bead height, and this is for micro hardness. So same thing I have plotted over here, so as to know how they are close to each other. Then I have performed optimization of process parameter with the desirability function. So these are my independent parameter, voltage, wire feed speed, and torque speed. These are the responses or dependent parameter, that is bead width, bead height, and micro hardness. So my objective function is to minimize the bead width because I want to deposit thin wall application, maximize the bead height, and maximize the micro hardness. That was my objective function. So after carrying this analysis, these are the optimal parameters. So voltage 15 volt, this is wire feed speed, torque speed, and these are the prediction with this optimum parameter with the desirability 0.662. So with this parameter, again I have deposited one more bead. So these are the optimum predicted values by the model, by the NO analysis. And after deposition, one more bead I have deposited with this optimum parameter, okay. So these are the actual values. So here the percentage error, that is also less than 2%. So these are the predicted optimum value, and these are the actual values of the response. That is bead height, bead width, bead height, and the micro hardness. After that, I have performed gray-based Taguchi analysis, because in earlier analysis, what happened? We have studied the effect individually. Here you can see width, height, micro hardness. But what is the exact contribution of this parameter? That we cannot identify with this method. So to know the exact contribution of each parameter, that is voltage, wire feed speed, and torque speed, I have done gray-based Taguchi analysis. So a lot of formulas are there. Then I have developed the Excel, and these are the readings. So I have performed the ANOVA analysis over this gray relation gray column, and this is the output. So this is the ANOVA table for that gray relation analysis. So here you can see from this study, we can find out the contribution of each parameter. So voltage has contributed 51.62%. Contribution of wire feed speed, that is 46.14, and contribution of torque speed is 1.84%. So with this analysis, we can calculate the contribution of each parameter. So it can be seen from the result that voltage is the most influential parameter with 51.62%. For wire feed speed, the contribution was 46.14, and for torque speed, it is 1.848%. After that, I have used an advanced method, that is a machine learning method. So I have used XGBoost algorithm to predict the values. So now these are the R square values for ANOVA. Okay, and then I have applied the XGBoost algorithm over the same table. So this was our table. Sorry, this was our table. These are independent parameter. These are dependent parameter. Okay, over this table, I have applied machine learning algorithm, that is XGBoost algorithm, and after applying that algorithm, these are the R square values. Okay, these are the R square values. And this is the graph between actual and predicted for bead width, bead height, and micro hardness. So now, then I have made comparison of this ANOVA technique and XGBoost machine learning algorithm. So these are the actual values taken by measurement. These are predicted by ANOVA, and these values are predicted by XGBoost algorithm. Then I have calculated the average relative error. So here, this is actual value. This is the value given by ANOVA. The error was 2% for bead width. For bead height, the error was 3.75%. And for micro hardness, the error was 1.43%. Okay. So these are our conventional mathematical modeling technique. It is analysis of variance. Now I have applied XGBoost algorithm. These are the predicted values. And now again I have calculated the percent error. So these are actual, and this is predicted by XGBoost algorithm. So here you can see the relative error. Here the relative error is 0.526%. Here it was 2%, and here it is only 0.5%. So these methods are more accurate than ANOVA technique that I have observed. For bead height, it is 0.7694%, and it is 3.75 for ANOVA. And for micro hardness, it was 1.43%, and with XGBoost, it is 0.8241%. So this is quite accurate as compared to ANOVA. Because here we are training that model again and again, and I think that is one of the reasons. So again, I have plotted and made the comparison between actual values, ANOVA value, and XGBoost value. So the last slide, that is conclusion. So the bimetallic structure I have deposited, which is made up of low carbon steel and ASS, that is successfully fabricated with the help of this cold metal transfer wire arc additive manufacturing technique. I have observed a strong metallurgical bond at the interface because no samples have failed from the interface. All the samples have failed in the LCS part. So there was strong metallurgical bond. The microstructural characteristics of ASS varied along the build direction with columnar dendrites. So mostly the microstructure of ASS, that was columnar dendrites, and it mainly consists of austenite and significant fraction of delta ferrite. So a duplex microstructure was there, austenite plus delta ferrite, while the LCS layer were comprised of polygonal ferrite and pearlite. Then EBSD analysis. So the preferred grain growth direction for ASS part, that was 001 along the build direction. Whereas for LCS, it was randomly oriented. So weak cubic structure I have observed, whereas strong texture I have observed in case of ASS. Weak cubic structure for LCS. Then the bimetallic sample fractured on the LCS side, which indicate that LCS side is comparatively weaker than ASS side. It has been found that the yield strength of bimetallic sample was greater than the yield strength of ASS. Okay, so bimetallic samples have shown more yield strength as compared to LCS, though the LCS was a part of that bimetal. Then a sharp increase in the micro hardness is observed at the interface of bimetallic structure. This is due to elemental diffusion because the chromium is diffused, nickel is diffused, and that was the result of concentration gradient and high temperature generated during the deposition. Then I have performed the corrosion test over the samples, and the IGC phenomena was observed. So intergranular corrosion was observed in ASS part. So the amount of chromium carbide that is least in the bottom part, highest in the middle portion. Then low corrosion rate and minimum degree of sensitization at the bottom part. Then I have performed the optimization, regression analysis I have performed to predict the correlationship between process parameter and build characteristics, to find out the relationship in between dependent and independent parameter. So this was the range of the parameter, and I have performed regression analysis over that. Then for single bid deposition, these are the optimal process parameters. So again, optimization was done, and these are the optimal process parameter with those objective functions. Then to assess the multi-objective performance of bid characteristics, Gray relation analysis was performed to know the contribution of each parameter, that is voltage, wire feed speed, and torque speed. So what we know, that voltage was the most important parameter, followed by wire feed speed and torque speed. Then I have applied XGBoost algorithm, and that demonstrates superior performance in predicting and modeling the build geometry in single bit deposition within WAM. So we can use these techniques. There are different algorithms. Those algorithms we can use to predict the output parameters. Regarding future scope, so in future, the upcoming researchers, they can deposit multi-material. I have deposited two different material. Now you can deposit three different material, and you can study its behavior depending on the application. Then you can deposit the material alternatively, because at VNIT we don't have that facility. For depositing the material alternatively, we should have two different robo. And I have gone through one or two research paper. They have in US, they have that setup. They have two different robos. So they have deposited the material alternatively, and then they have studied its behavior. Then we can investigate the effect of heat treatments over the deposition, and then we can apply some other techniques, other machine learning techniques like decision tree, random forest, linear regression, artificial neural network for predicting the bid morphology. And we can show their comparison. So this is from my side. Thank you so much for your patience listening.
Thank you, sir. I think this is a new topic. Now I open the session for question and answers. If participants, if you have any question, please you can unmute yourself and you can ask a question. Raut sir,
Yes, sir.
one of the question, yeah, Mari Prabhu Govindam sir, can you unmute yourself and can you ask the question?
Yeah, good evening, sir.
Oh,
Good evening.
sir, good evening, good evening. Please ask the question.
Sir, your session was very wonderful, and
Hey, your voice is breaking.
I started my course for learning device, which are affected with additive manufacturing.
Sir, your voice is breaking, sir.
Hello.
Hello. Okay,
Sir, can you hear me now?
yeah, right now, I can hear you.
Yeah, so I just wanted to know, can you print additive device with biotechnique, which you were teaching us just now?
No, you are not audible. Means your voice is breaking. You can ask your question in chat section.
In chat section, he typed, Raut sir, if you see it,
Uh-huh.
then he's asking, can you please help me to print aluminum alloys and nickel-based alloys with a WAM?
Yes, yes, sure. We can, even in VNIT, my colleagues are depositing nickel alloy. So we can deposit nickel and aluminium. It is difficult to deposit aluminium because there are certain challenges. But then, yes, definitely I can help you. You are welcome. At VNIT, we can try. We can take official permission from the VNIT and we can try for the deposition of steel and aluminium. Sorry, nickel and aluminium.
He's asking your contact.
Okay. Please note down my email ID. It's laukik.raut@raisoni.net. laukik.raut@raisoni.net. raisoni.net.
Uh, I've entered in the chat box.
Yes.
I think one more question from Dr. Dilip Kumar Biswal. Dr. Dilip, can you please unmute yourself and ask the question?
Yes, sir. Thank you, sir.
Okay.
Is it audible, sir?
Yes, sir,
Yes,
audible.
sir.
Perfect.
Yes, sir. Sir, by using CMT, is it
Hmm.
possible to join two dissimilar materials?
Yes, sir.
Because you
Even I
have
have.
used, I think,
Hmm.
stainless steel and two metals.
Hmm, hmm, hmm.
Whether it is possible to join like two dissimilar metals and you can weld it.
Yes, sir. It is possible. It is possible, and it is
Possible, but
known for its. Hmm.
yes, sir. Yes, sir.
Mostly the CMT is known for low heat input. So we can take a
Yes, sir.
benefit
Yes.
of that, and it is possible to weld two different material with the help of CMT. There are certain challenges like aluminum welding is always difficult because there are certain challenges. So, but
Yes,
it is
sir.
possible. We have welded steel with nickel.
Yes, sir. Yes, sir. Okay.
So it
The
is possible.
strength-wise, all the characteristics, it will be affected or
strength wise.
Yes, yes.
Yes, the strength
If
is
you compare
mostly.
to the parent material,
Mhm.
whether the strength will affect, I think it will increase. I hope so.
Strength will increase, but again, it depends on the independent parameter like what current we are using, what voltage, wire speed. Those
Okay,
parameter will also play an important role, but the strength will increase.
okay.
Because even
Thank you,
in
sir.
my case, I have joined LCS with ASS, and all the samples
Yes, sir.
were fractured in LCS part. No sample failed
Yes,
in
sir.
the interface. So the strength
Yes,
is
yes.
obviously increased.
Okay, sir. Thank you. Thank you, sir.
Welcome, sir.
Uh, so I think there is another question from Shinde. Shinde sir. Shinde sir, can you unmute yourself and can you ask yourself? Shinde sir. Am I audible? Raut sir?
Yes,
Hello.
you're audible.
Hello.
Yeah, madam. Sorry. Yeah. Sorry.
No problem. Sir, suppose we are synthesizing new alloy, means
Mhm.
new composition we are taken and that is we are synthesized. Then how one can find its electrochemical potential?
We have a setup for finding out the electrochemical potential, ma'am, at VNIT. So
Okay.
uh,
Just two electrode geometry or there are required three?
that complete setup, I'm not sure about it, electrochemical potential, but then we have a setup, ma'am.
Okay. But as per solution, it will be different values we are getting if we
Mhm.
consider in corrosive medium.
Basically, you are synthesizing two different materials, so obviously you will be getting two different values.
Okay. Thank you, sir.
Okay, thank you.
Sorry. Raut sir, there are few questions from Chetan sir. Can you unmute yourself? Dr. Chetan.
Okay, he has suggested that he has already joined two
My
different
voice is
material. That is,
audible.
Yeah, now it is audible.
Actually, one question is there from the participant that two dissimilar materials can be welded. CMT, it can be welded.
yes.
So this paper, I
Oh,
have
oh, yeah. Okay, okay.
this
Thank you.
paper,
Thank you. Yeah.
the participant can refer this.
Okay, thank you for sharing, sir. Thank you for
In
sharing.
VNIT itself, we have performed this welding.
Yeah. In VNet,
316L and 430. We have
yeah.
welded.
Yeah.
Dr. Praveen Kubde also wants to ask a question. Dr. Praveen, can you
Yes, sir.
unmute
Yes,
yourself?
sir. Yes,
Okay,
sir. Yes, sir.
please. Yo, please go ahead.
Okay, okay. Sir, while telling about the second conclusion, you said that a strong metallurgical bond was observed at the interface
Mhm.
of those materials. So, can
Mhm.
you elaborate the physics and chemistry behind it?
Okay. So that I have concluded from that, like all the samples, they were filled in not at the interface. They were filled in the LCS part. So on the basis of that, I have concluded that there was a strong bonding between LCS and ASS, because I have deposited two different materials. So based on that, I have concluded that there is strong metallurgical bond, and there was no defect at the interface. So because I have observed through optical samples I have taken, then SEM samples. So there was no any defect, because the papers which I have referred earlier, few people have observed defects at the interface when they have deposited different combinations like steel and nickel. So in that case, they have observed some defects. So in my case, there was no any defect like porosity or some other defects. And then no samples were fractured at the interface. So from that, I have concluded that there is a strong metallurgical bonding.
Dr. Praveen, is it?
No, actually, a defect is something different, but I want to know a little bit more about the chemistry behind it. Why actually the bond form was stronger?
Mhm. No, the means I have concluded as the samples were not filled. That is why I just concluded that there was a good bonding. I have not gone through its physics or chemistry, simply.
Yeah, well, mechanical testing you might be concluded,
Huh.
right?
From mechanical test only, I have concluded.
Yeah. Raut sir,
Yes, sir.
there are another question from Kiran Kumar. Kiran
Hmm.
Kumar, can you unmute yourself? I just
Sir,
want to ask. Yeah, please proceed.
sir, you have done on the steels now, sir.
Yes,
Can
sir.
we apply these techniques on the aluminum, sir? Is it
On
possible?
aluminum also we can apply. I have gone through several papers where the people have deposited aluminum as well.
Okay, sir.
Okay.
Okay, sir. Thank you.
Okay, Dr. Pratibha Nikam, ma'am, you raised your hand. Can you ask the question? I mean, do you want to ask the question or?
Yes, sir. Actually, it might be simply little bit out of topic, but I just curious about it. Since I just want to
Hmm.
ask about the thing. Uh,
Hmm.
you work on the combination of two different metals. As per my understanding, is it okay? No, means I think I
Yes,
just think.
yes, ma'am. Yes, ma'am.
So, can we go through that particular corrosion, erosion, all these things? Means, can we simply coat the gelatin-like layer on that particular same material? By means, we can avoid the further the uh, that particular rusting or corrosion of all the
No, ma'am.
material.
That can be one of the solution, but see, the application, it depends on the application, because they are subjected to harsh environment,
Yes.
and there the corrosion is very big topic. So there are various phenomena like intergranular corrosion, after that pitting corrosion. So intergranular corrosion that occurs on the grain boundary itself. So for that purpose, we need to study all those. We need to carry out all those tests.
Yes, sir. And the another one thing, as previously someone was asking that particular chemistry and physics behind the combination of two materials, it might be sharing and pairing of the electrons. Could it affect on that particular phenomenon? I just think in that way.
Actually, I have not gone through that chemistry because I am from the mechanical background. So I
Yes.
have not gone through that chemistry part. So that is why I'm not able to answer that strong metallurgical bond, because chemistry background is needed for that. I don't have that background. So simply from the uh, tensile test result, I have quoted that statement. I wrote that statement there.
Yes. And as
Raut
previously
sir,
you, uh,
sorry to interrupt. You
may I
please go
continue?
ahead.
Yes, sir. As previously you told that particular combination means we can go through the 2 to 3 materials at the
Mhm.
same time we can combine.
Mhm.
Rather, you were telling by layer we can go through, or a composite we can make and then we can deposit or form that particular whatever the beads
No,
or.
no.
Yes.
Even layer by layer we can deposit. Now people are depositing, means one layer of say steel, another is of nickel, again steel, then nickel. So right now people are doing depositing like that, because in every layer you are getting different properties. So depending on the application, you can use that material.
Yes, thank you, Saji. Really, session was very nice because it is just means that particular area is not my expertise or
Mhm.
all things, but really it is very informative. And simply that particular Praveen sir, I think so, asked about that chemistry. So any chemistry person can approach in that particular way, and he or she can
Yes, ma'am,
study all
sure.
these things with your uh, isn't it concern, and they can solve that particular issue, isn't it? Might
Right,
be
right, ma'am. Right.
very effective.
Mm-hmm.
Thank you very much.
Thank you, ma'am.
I think, see, there are many participants from chemistry and chemical background. They can take the study further, right, Laukik sir?
Yes, sir. Yes.
Because some conclusions that lead to some new problem statements as well.
Right.
So,
And that can be a future scope as well.
yeah, absolutely. It's never-ending process, basically. We cannot
Yes.
conclude at one particular conclusion. It always leads to some another area.
Right.
Okay.
Because because there might be some van der Waals forces, there might be some different chain reactions. I
Mm-hmm.
also belongs to mechanical engineering only, but
Mm-hmm.
still I want to know a bit more about those things
Mm-hmm.
because I
Actually, sir,
also work on. Hmm,
right, sir. But my
hmm,
focus was on not on that part. My objectives
hmm,
were different. The
hmm,
machine learning techniques, optimization. So after that, I have focused on those parameters, those
hmm,
objectives.
hmm, hmm,
So,
hmm.
but in future, definitely, I will work
Because
on
that
that.
that
And
thing, when we conclude or when we make a statement, a
mm-hmm.
strong bond was formed between two materials, then I
Mm-hmm.
think we should know why the bond is forming. What is the actual chemistry or physics behind it?
Yes.
What are the things those which are influencing, like van der Waals forces, maybe different thermal coefficients, or etc.
Mm-hmm.
etc.
Mm-hmm.
That type.
Oh, uh, I think,
Okay, sir. Thank you from my side.
thank-
Once may I interrupt that particular discussion?
okay, ma'am, please.
Actually, as sir told that particular thing, yes, sir, there is definitely a chemistry and physics behind it because na once means if you are going with the two different materials, we have to think about all the parameters, basic parameters which we can use while synthesis or deposition or anything which we can do with that particular material. So ultimately that chemistry matters here. That's why I asked that particular question. Shall we go for layer by layer, or we means it will be better to make a composite and then we can take a deposition, isn't it? So ultimately the number of forces and number of bondings and all these things means strengths in terms of the tensile or whatever be the strengths, ultimately it will affect that particular deposition.
Right, ma'am. So this can be a research topic. So whether we have to go layer by layer, or we can deposit, we can develop a composite. So it's a topic of research. We can explore it more.
Yes, sir.
Uh,
Sir,
Okay, sir.
methods may
Overall,
be
the session was
sir, methods may be different,
Mhm.
but still, all entire material science is all about the chemistry and physics only. So we asked that question.
Yes, sir. Yes, sir. No,
Uh,
no
uh,
issue.
uh,
so, I think we should conclude because we have a next session in line. I think because of, I mean, based on the discussion, I must say that Dr. Raut, your topic was very informative and your work is commendable work. That's why I think you got, I mean, more than 700 citation in a very less time. And also, the people are also interested because it's an entirely new area. Thank you for your insights on the functionally graded materials. Your sharing of knowledge definitely help the participant to take the study forward, and it must enhance their learning as well. So, thank you, Dr. Raut, for
Thank you, sir.
joining
Thank
us.
you.
Okay.
Thank
Uh,
you so much.
Dear participants, the next session, the speaker for the next session, Dr. Mahesh Kore is also joined, but some of the participants, they are asking for uh, 2 to 3 minutes of break. Kore sir, can we take a 2 minutes of break? 2 to 3 minutes of break?
Yes, sir. No issue, sir.
No issue. No. Okay, okay. So now it's 7:36 in my clock. We will sharply start the session at let's say 7:38. 2 minutes break or 5 minutes break. We'll start at 7:40 sharp. And I request participants don't leave the chat. The meeting. Be there. Just refresh yourself, and we will start at 7:40.